So for this last session of the day, we'll be talking about an introduction to Julia, which quite recent programming language compared to all the others that you saw, except maybe for Rust. But compared to C++, C, Fortran, or all the other languages, Julia is a rather young language. So I will follow the following plan for today. So it will be a primer with the general history and why Julia is interesting for scientific purposes. We will speak about variables and types also because there is a specific aspect in Julia for this. Some functions, and for the last item, we will open up a notebook on Colab, and you will see how we can manipulate variables and how to make a matrix multiplication in GPU on Julia. So the Language Foundation was in 2012. It started from a work for 4 persons: Jeff Bezos, Alan Edelman, for the most known ones, Stefan Karpinski, and Vida Plas, and it was an association between Yale, MIT, and Berkeley. Also now there is a French group working on Julia also. French people have been very active on the language, especially the École Normale Supérieure at Paris, who is some teams that worked on the Julia parser. We will see that in details later on. The key date for Julia from 2012 to 2019 is about the version 1.0, which set actually the background and the usage of the language. So at this time, actually, Julia got more and more interest from academic people, from industry also, as a stable language, and was actually the real date of the kickoff of the language. Actually, today we are at this version 1.11.5, and you can find a lot of documentation on Julia Hub and also the Julia language discourse with the links just below. So Julia is a high-level programming language, similar to Python or MATLAB, actually, but with the aspect that it was aimed actually to be fast. Okay, so the target of Julia, the aim of doing this language, is to make a high-level, easy, between brackets, programming language, but that computes, that executes, that infers very fast, like C, C++, like Python. So of course, this target is not reached all the time because you need to do a lot of optimization to do that, and especially because these 3 languages, Fortran, C, C++, has been optimized for a long while ago. So it's very hard to reach these performances. But we still get there. The only thing that you will get more in Julia over these languages is the maintenance easiness. Okay, so the readability of the code is easier. It reads like Python, actually. And the Python community and Julia community are very close one to the other. So Julia is just-in-time compiled. So there is an example in Python for this, is the Numba library, which is also a JIT library. So you can optimize it very easily on different platforms. It has a memory garbage collector implemented natively in the software. It's dynamically typed, but it's different than Python. We will see a very harsh example on this, on how you can do these types in functions, actually. So this is very, very tricky in Julia because it's more static than dynamic in some way, but it gives the easiness of dynamic programming. And also it's object programming like Python. So just-in-time compiled, Julia is composed on two big flow rates, let's say, the runtime and the compile time, actually. And what you see here is something tricky, is that you don't have to execute your code. You don't have always to go to the compile time, to the compile one, okay? So this is very important. The parser, so before this layer, there is what we call the parser, actually, that reads your code and sets up the variables and sets up the memory and all the stuff. The parser decides whether to go through runtime and where to enter the compile time and exit from it, okay? That's why we will see that in an example also. When you execute Julia for a function, for example, first, you will always go to the compile time. Okay? But if you don't change the typology of the function or the typology of the variable of that function, actually, what will happen? You can go directly to the runtime. So the parser work is to do this, to analyze whether you have to go to the runtime directly or whether you have to go from the runtime to the compile time and back to the runtime. Okay? So this is one of the advantages of the language. So this is very complex, of course. We will not get into these details. But I put you here a link to one of the founder of the parser of Julia. There's a video there that explains very well, actually, how this works. And we will see it also through the dynamic typing of Julia in the example we will see later on. Okay. So some comparison of Julia with other languages. So this has been micro benchmarks. So on specifically targeted small algorithms, not on big codes, on all the stuff. So usually we are close to the half of what we can do on C. We can get close to C, but not that much. Sometimes we are below C, but these are very specific optimized codes. So this benchmark has been done 4 years ago. Okay, there has not been another article speaking of this recently, but still it gives you an idea of how fast Julia can go actually if you code it correctly. Okay, so these are very known algorithms. So this is one of the classic benchmark that we use for benchmarking codes. Okay, so we're not all the time as fast as C, but we're getting there more and more. C, by the way, C is the reference for speed. It's not C++ or other language. Okay. So it's a general purpose programming language, okay, but not as Python. You cannot do easily web interfaces with Julia. You cannot do finance as easy as you do it in Python. You cannot do, I don't know, network programming or all this stuff. So it's more, how to say it? It's a language done by scientists for scientists. So it's more an academic work. The only external usage to academics that has been used in Java is for finance, for trading, for example, because it's fast and easy to maintain. So this is the only use case, very known use case, but I don't want to cite it very much because it's not my field. Okay, but what you have to keep in mind, it's more an academic software, so it's done by scientists for scientists. It's a high-level and high-performance programming. It offers actually generic programming and polymorphism also. You can have a lot of easy data model extension for operation of use, so ease of operation. The packages are starting to be very, very rich. Not as rich as Python, of course, because the Python community is much larger than Julia. But you have all the deep learning and IA libraries available. You have a bunch of packages to solve differential equations, like the one we are solving here in Grayscott. You can do algebraic computing, and the advantage here is you have integrated parallelism with multithreading and GPU support. So this is multithreading was natively done in the language. GPU has been added afterwards. So developing in Julia is easy. You have many ways to develop under Julia. So you have the interactive text interface, the REPL. You can match it by the command line. Just type Julia, it works. There is a package manager also. You can use it with Visual Code, for Emacs, Vim, and also for Jupyter Notebook. That's the case we will see today. So something to notice, Julia was a native language with Python and R for Jupyter Notebooks, actually. So there was 3 native languages supported by Jupyter, R, Python, and Julia. And since March 2029, so this is quite recent, 3 months ago, you have a direct integration in Google Colab. So if you want to access a GPU for free, for example, you can use it directly on Colab, Google Colab, and that's free of charge, of course, for half an hour or an hour if you use a low-level GPU. So this is what we will do actually later on Colab. So this is to say that the language is extending its use, but still it is in the scientific community. Another advantage is the multiple dispatch. So we will explain this later on actually with a specific function. I will give an example of this. Julia offers dynamic dispatch actually for all function arguments, and this is called multiple dispatch. So you can change the function and the arguments. Okay, so this is very useful. So if you developed a complicated function for certain type of variables, actually you can easily reuse it actually for other type of variables. So extremely effective in allowing reuse of code developed by others. So this is for code shariness. There is an example here of multiple dispatch actually. And why, actually in this video, it's explained why this multiple dispatch is very, very powerful actually. And it's kind of unique something in this language. The types. So this is the architecture and the graph of all the Julia variable types. So they are very well determined. So the tree is very specific, starting by any and ending to all the types that we use in usual programming. So the multiple dispatch of function actually is closely related to this. So we will see later on a tricky example of this in the notebook. Okay. Debugging and profiling tools. So Julia provides a rich set of debugging and profiling tools, as does the Python environment, as exactly the same. But the other advantage is that you can add macros in your code. For example, in the Jupyter notebook, we will see this later on. And you can see actually what has been compiled specific to your function or what you did. So this can be very, very easy actually if you want to optimize some function or to see what's the best way to write a function actually, and to see how the compiler actually will execute it. So the code type and the call LLVM actually are very useful for this kind of purpose. So debugging is easy with interactive languages. You have a debugger that is included also in Julia, which is the library debugger.gl. There is a profile that is native in the language, but you can use actually profilers from CUDA or from other actually specific libraries. That also works. So you have for GPU. So this is the example we will see later on for matrix multiplication. So there is almost 300 Julia packages using GPU. So it's a massively. There's a lot of libraries that are handling GPU natively, so you don't have to do it, they do it for you. One of the most famous libraries in Julia for GPU is the CUDA.gl, but there is also support for one API and AMD and macOS with the Metal language actually that specific to their new computers. So I don't use it, but I know people are working on that, so that seems to work, getting some advancement on it. So there's two kind of programming options. You have the array programming, so this is the easy path. That's what we do with the other languages. So it exploits Julia power of code reusability. So when you do this, actually you can reuse code very easily. But you can also develop custom kernels in Julia to allow best optimization. So it's a balance between reusability of the code and optimization, as always, actually, let's say. Okay, but this library is really working well, actually, for the NVIDIA support. Julia is also compatible with other languages, like C, like Python, C, and Fortran. So these are wrapped very easily. The only issue we have is for C++, which is always harder to wrap for other languages. So there is some work with some colleagues, like Philippe Gras is working on this, on automatic wrappers for C++, but this is not optimum yet. So if you want to wrap an existing code, so for Python, it should be flawless. For C also, For Fortran, it works. I didn't use it myself, but for the other language, for C++, it's still, I don't advise you to do that, actually. So going from C++ to Julia is not an easy task. You have to spend some time on it, which is sad for the moment, but that's specific to C++. But in any case, the advice here is if you want to really optimize your code, actually, you have to recode it in .gl, in the Julia native language. Even if you can optimize code in C, in Fortran, actually, the best way for the parser, actually, and the runtime and the compiler time, specific use, actually, of the parser is to recode your program in Julia. It's always advice. So you will always get better optimization, actually, without the wrapping. So it is possible, but it's not the best way to optimize code. This has been done also actually to get people from the other communities getting easily from Julia. But, okay, so for the installation, actually, it's quite easy. So it supports many kinds of OSs, Windows, Mac, Linux, ARM, whatever you want, GPUs on NVIDIA, AMDs, Metal for macOS also. So very easy to install. So you go to this web page, actually, julialanguage.org/downloads, and you just choose the version you want, actually. So for Linux, it's very easy to install, so just one command line, and you get Julia working. So when you have this, actually, it depends also in what IDE you want to use. So there is some specific documentation for every IDE, okay? So the documentation is very rich and very well done, and that's regularly updated. So you will not have much problem actually getting the information on how to install Julia and make it run. You can nuke it through Jupyter kernel, actually. So this is the procedure of the install. So you have to add the package, which is iJulia. And you can run it from there, actually. You can also add the Julia package manager to this command line, actually. And it's very easy to import packages in it once it is installed. So what you have to do is just always keep the package manager updated so it can link the version of the libraries very easily. Okay, I had one of these bugs lately, actually. So for this tutorial, actually, we will be using GPU and Google Colab because I checked it worked very well. It will be not depending on your machine. Okay. So and in the case you want to use it with Jupyter, so in case when you type this command, in case Jupyter Lab is not found, actually, it will prompt you to install it automatically. Okay. So either use it on a web interface with Google Colab on a Jupyter on your machine. But you have to make sure that you access correctly to your GPU and that your NVIDIA driver or whatever you are using as a GPU works correctly for Julia. So we have a test to do this, to check if the GPU is accessible. If you want to do some GPU computing, it's mandatory, actually, to get it to work. So for easy of work today, we'll do it actually through Google Colab. So for getting help, so you type something and you put a question in it, actually, and the REPL, and you get the help automatically. So that's very easy. You have the Julia manual, actually, and you have various channels on Discourse, on Slack, on Zulip. The Julia Hub is updated quite often, actually, for all the libraries that you can be associated with Julia. And you have also the Discourse page where people interact together, actually, to solve problems in Julia. Okay. Also, there's a lot of documentation, of course, on the internet through your best AI or your Google or whatever, actually. So it's a well-documented language. You usually not have a lot of problems to get help on it for debugging, of course. Some example of large Julia codes, actually. So since 2019, there is a big collaboration in the US, which we call the Klima code, actually. And this is a huge work, actually, of recoding a climate code from scratch and without using the old climate code that had been developed. So you know maybe that climate codes worked on Fortran mainly. Okay, so these codes have been developed by a lot of researchers and scientists, like for 50 years or 40 years. So they're very hard to maintain, and there's also very hard to benchmark. So there is a lot of work done by Julia community for this. So the two libraries are ClimaCore and ClimaMachine, and they are benchmarking like any function of a climate code one by one. So for example, here you see the convection between an ocean interface and the atmosphere. So they take it, they recode it, they compare it to a previous Fortran code that is doing the same thing, and then they validate if the code is correct or not. So the only advantage you get, the main advantage you're getting by recoding this is the maintainability and the readability of the code over time. Okay, so so thank you for listening to this small introduction to Julia, and special thanks to Philippe Gras also, who did this introduction in 2023, so 2 years ago for Julia. So now I will switch to the Jupyter Notebook to see some examples. So this is not the page. So is there any discourse question yet or no? No. So this was for Adrien. No? Okay. Okay. So Jupyter Notebook on Colab. So I'm connected to runtime. So as I said previously, since March 2025, so 3 months ago, you have a direct Julia support in Colab. So how to do this? You go to execution runtime here, and you click on modify the runtime, and you'll see all the languages that are supported here. You have Python 3, R, and Julia. So Julia was not present before. You had to install it manually in the notebook itself. Now it's present automatically with the latest version. And you can associate it with any parallelization support you want. So you can do it with TPUs, with GPUs, with processors. So for myself, I tried it with GPUs only. I didn't try Julia with TPUs on other accelerators. I don't know if it works or no, but these are specific to deep learning or AI libraries. Okay, but for matrix calculation or parallelization or this kind of work, you can use all the present GPUs you have. And if you have a large problem also, you can ask for a bigger memory access. Okay, so for the first parts of the notebook, we'll be using the CPU. Okay, just to use the basic language. And after we will switch to GPU for specific problem on matrix multiplication. The idea here is not to give you all the recipes, but to give you one example actually on how the type statism or dynamism works in Julia, and what's the difference between dynamic function, static variable, and dynamic variable, and also how to make well, very easily multiple metric multiplication on GPU. So moving data from CPU to the GPU, make the multiplication, and get back the data. Okay, we will not use profiling here because it's out of the scope of this presentation. So first here we define a variable. Okay, we can get its type. So it's an int64 here. We can ask him to print a string with a random number. So the random libraries are the same that are used with Python. You can use stride actually with them to make sure that the numbers are the same. These are really, for Python users, are flawless. I mean, it's the same, almost the same syntax. Okay. Here we will define a function. So there's many ways to define a functions like as Python. So here we define a function square. Okay. We make the computing square of 2, makes 4. And here actually we'll try to get into inside. Yes. You can see from there. Okay, sorry. Okay, better? Okay. So here actually, if you type this micro here at code typed square 2, you can access to the code that compiled actually to see what happened. Yes.
I see when you define a function, you use end at the end.
Yes.
Do we have to put the return with a...
Good question. It's an example that will follow in a few lines, actually. Okay? So I did, yeah. You can use it without the return, but you will see the difference. Okay? So here we put the return, actually. Okay? We see the generated code here. Okay? And here I tap the function without the return. Okay? So we will execute it. We will see what gives us in this line. Okay, so this is the code generated by square of 2. Now I use the same function without the return. Okay, I execute it. Normally I should get the same result, but if I see what the code generated is exactly the same. So this is the job done by this parser. Actually, it understands that you define the function and that the x square is a return without you having to put it manually. Okay, and the best way to compare this is to see what has been compiled early. Okay.
Is always the last line of the function?
Sorry?
Does it understand always the last line of the function as a return?
If it's not clear for it, it will ask. It will give you an error or ask for it. Okay.
Yeah, but how does it figure out? Is it the last line of the function?
No, it can be actually, we can return many variables, not the last line. Okay, so it will interpret what are the inputs and what are you returning. Okay. So we will have an example with variable types later on. We will see a specific example for this, for multiple dispatch actually. Okay. So you can type it also like this. It works the same. So I didn't generate the code generated by this, but gives you the same result. So just way to say that there's many ways to write function in Julia, and this is the same thing that you find also in Python. Go ahead.
Is the indentation necessary?
Yes.
As long as we have
best.
an end.
It's better. Actually, I never use code without indentation, so I don't know the answer for this question. But if you want people to read your code, do the indentation.
Yeah, but it is necessary in Julia.
Normally it is, yes, like Python.
Okay.
Actually, I think I didn't try it, but it's a good exercise. You can take the notebook, delete the indentation, and try to execute it. But for myself, I never did this actually. Okay, so if you share codes, you do the indentation. Okay. Yeah, so we're not beyond best practices of writing code, of course. Okay, it's not because you have a good parser that you have to write anything anyway. Okay, so you have keep also in mind that your code may be taken by other people and to make the code correctly. So when you define a function like we did here, you not specify. You don't need to specify the arguments. It will try to guess it actually. So this is somehow the Python way of working. Okay. Except for code specialization when you need a different implementation for a specific set of arguments types. So we will see an example of this. So it's not always used to recommended to specify the types, but if you do so, for in this school actually you saw a lot of compiled languages. You saw also some interpreted languages. You know that for compiled languages it's always better to specify the type and to control it yourself. Okay, and this is also the case for Julia somehow. Okay, so you can have other types than the simple variables. You have structures actually here. So in this example, we don't define the type, but we can also define it with the type. Okay, so to keep the performance, the type must be concrete. So if you go back to my slides, so say there is some abstract types and there is some concrete types. So for performance, it's better to keep the types concrete. Yes.
So here writing the type of your different variable is useful for performances?
Yes.
Okay, so
Yes.
it's not like Python.
No.
Okay.
But you can do it also on Python.
Yeah, but it's just like
Okay.
for documentation and,
Yeah.
and legibility. And here it's used by the compiler to optimize.
Yes,
Okay.
to allocate the memory also.
Okay. Okay.
Okay. So yeah, it's important. In the case of Julia, it's important. Yes.
Okay.
Otherwise, it's waiting
Sorry?
to. Otherwise, it's waiting to know what.
No, otherwise it will take the maximum.
Okay.
Okay. So it's not the good way to do it. Always specify your variables actually, unless you really don't know what will be the output or something like that. Okay. Try to reason with it like a compiled language. Maybe it's the best way to do it. For Pythonists, Python users, when you go to Julia, try to use it as a compiled language because you will get the better performance. And actually, it's not specific to Julia. For all other languages, actually, try to specify your variables. It's always good. We can also choose another type of variables that you define yourself. So this is as specific as all the other languages. You can define actually dimensions and arrays. This is an example here. So we defined an array with 3 floats, 64 floats. Okay. Very easy to do. So this is all Python-like. You have the fill function here, which we are testing. Okay. So just we define the array and we say fill it with 3.4, but with pi actually on the x size, y size, and z size. So all this is flawless right now. Okay. You have the, like I said before, the random generators also that can use actually to fill matrices. So this is useful also in many cases. So float 64 and you fill all the matrix with it. Okay. And you can also use undefined if you don't know what variable you want to put in something. So it will allocate some space. And it also works very well. And you can actually fill this variable later also. Okay. Okay. You can also check the compatibility of types of variables. So here we have a vector of float 64. Is it same thing than an array of float 64.1? And actually, Julia will interpret it as the same thing. So it's smart somehow to do this. And this also works with vectors, but it works also with more complex types like matrices, actually, to see if you are working on the same object. And you use actually the word vector actually is an array of 1. And you can use it in a function. You can just give a vector, okay, or you specify an array. And Julia would understand it as the same thing. So the function will work with the two because the parser of Julia will check this automatically. If you define a function with a vector, for example, but you decide instead of running it with a vector, you want to run it with an array. If the array is the dimension 1, it will be accepted. If you put the dimension 2 to array, it will not be accepted. You see the difference or no?
All the matrices assumed as 2Ds?
Actually, this is a good question. Matrices are maximum 3 dimensions mathematically. After higher than 3 dimensions, we call that tensors.
Yeah.
Okay? But in the absolute, tensors are matrices with higher than 3.
How can we know matrix of float 64 is 2D or 3D?
Because it knows the dimension of the matrix when you define it, actually.
But here you're checking if matrix
yeah, I'm stressing that the matrix
2D.
is something that an array is the same type of an array of 2 dimensions.
Okay.
Okay. And that also works with tensors. Okay. So there is another way also to define big dimensions or big other type of data. It's using the data frames. Actually, this is very easy also. You just have to import the library. And you can define a data frame. So with bigger data frames actually will lead you to tensors anyway, okay? In this way, actually, and it works like an array or like a vector or like any other object. So there is, how to say it, there is an intrinsic compatibility between types of variable in Julia. This is what we want to say. Okay. You can do also some broadcasting on a matrix or on a vector, whatever you want. So if you define a matrix like this, 3 by 2, you can do the square of this matrix actually automatically. Julia will understand that you want to broadcast all through the matrix. Now for JIT compilation. So here I give you an example of how to monitor time. Yes, go ahead.
Yeah, sorry, I just have a question about the functions that you used before.
Yes.
Do you have to import some libraries like in Python to use like square or random, or is it standard function in Julia?
No, in Julia. It's,
Okay.
No, it's recorded in Julia actually. They have, yeah. So this is misleading. Almost all the Python function have been recorded in Julia, but in the Julia language itself.
Okay.
So they keep the same name, but they are not native Python.
Yeah,
They are
sure.
really. It's not a wrapping. It's really actually the real extension is dataframe.gl.
Yeah, no, well, my question was like, do you have to import Julia libraries to have access to random, to rand, for example?
No.
Okay, so
No.
it's natively inside.
Yeah.
Okay.
Yeah. Rand
Okay.
is natively in the.
Okay,
in
it
the
was my
language.
question.
Yes.
Thank you.
Yes.
Yeah.
But not all the functions are okay. Yeah. Okay. So where were we? Square. Okay. So we go through the JIT compilation here, and after we will have an exercise on the typing and the statism of functions and variables also. So here actually we try to monitor the time that it takes to make the sum. Okay. So I run it first. You see. Okay. If I click back to the on the play button here, you will see that the time changed. So the first time you go through the compiler and the runtime. Okay. But the second time, if you don't change anything to your function, you go directly to the runtime. And here that we will see that the time actually changed a little bit for the second time, but not that much. Okay. So if I run it again, it's almost stable now. Okay. So always when you run a function the first time, that's not the real time of its execution. You have to run it twice for that. So this is quite weird in Julia, but with time you get used to it. The first run, you go to the compiler and to the runtime automatically for the first time. The second time, if you didn't change anything to your function, you go directly to the runtime. Okay? Sorry? Yeah, for the whole cell. Yeah. It checks the function actually. This is mainly for function actually, the runtime and the compiler. So for function, if you didn't change the type or the topology of your function, the parser will analyze it and will say, no, this is not modified. I can execute it, run it directly. Okay. This is the schema I gave you in the presentation when you see where you go into the runtime and when you go to the compile time. Okay, so this at time macro is native in Julia language, so you don't have to import it. There is another package which is called benchmark tools, okay, which is more performant because here when you measure, actually you measure a lot of variables that a lot of processes that are in the environment itself, okay. The benchmark tool is much more precise, so I have to import it in this case. So it takes a little while, but it will give you the runtime actually just for your process, just for the function you run, okay? You have just to wait like maybe 20 seconds so it installs. And you will see that where is the difference between the upper one and the second one. So if you want to go through precise profiling of your functions or your executions, actually, it's better to do it through this library than the native Julia one, okay? So with this one, if you have the same environment, normally you don't have a lot of variability, which is the case for the other one. Okay, so now we'll do it here on this line. So instead of using at time eval sum, I use b time eval sum. Okay. So I just run it. Weird. Okay, so if I run it again, normally I should have a stable time this time. And after we will double the number of items of the sum. So I had 69 microseconds in the first run. This time it's 78. So it doesn't move that much. So it's tagged really to the compiled part of this specific code. So if I take off the commands here and we do it again, so the more time that you'll see is because of the library itself for the profiler, actually. Okay. So almost no difference. Okay. So if you want precise profiling for your functions or multiplications or whatever operation you do, it's longer, but it's always better to use the benchmark tools library than the native actually timer that is set up in Julia. Okay. So this is feedback from the community, let's say. Okay, now let's get some harsh example. Okay, we spoke about dynamic typing and static typing in Julia. So here, I put you a function here, a loop, okay, with two variables, n and r, and that is defined out of the function. Okay, and the question is, what is the type of n? So does anybody have an idea? So when I say what is the type of n, what is the type of n at the variable step of the function? Okay, so here n is still an integer. Okay, I go here, r is 0, so let's say r is an integer also. And we say while n is superior to 1, we add 1 to r, so we increment it, okay? And we divide n by 2, okay? So at the beginning, Julia says sees n equal 5, basic, so it's an integer. Why put it in as a float? We put it as an integer, okay. Okay, so the function returns here r only, all right? So the function is static. We give it an integer in the input, and we have an integer at the output. The function is static, but are the variables static or no? Does anybody has an idea? Wait, think. It's a tricky problem that you have. So in compiled languages, in compiled languages, we don't have this issue because you have to define the type of your variable. And if you put n as an integer and you divide it by 2, if it's not pair ou impair, I don't know how to say that in English. Yeah, that's it. Actually, you have to change the type and you will have an error here at compilation, okay? Well, Julia doesn't give you an error, but what happens behind the scenes? So the function is static, so we respect that, okay? Because we are turning r as an integer. So, but now tell me what happens with n. Does anybody have an idea? Okay, so we'll do it step by step. So the indiv function, so I call this because we divide an integer, so that's why I call it this way, okay? So here, n is an integer. We enter the function, we define r as an integer also. So when we enter the while, n is still an integer, okay? We increment the r, okay? And we see n equal n divided by 2. What we do, actually, what will Julia do, it will make an union type between an integer and float 64, okay? Easy. We say, okay, we're not sure of the type. We change the type of n. And at the beginning, it wasn't an integer, but in the loop, it becomes a union between, so a mixed type between an integer and a float 64. Let's say we decide later, actually. Okay. But, so the function is type stable, but internally, the function is not type stable, actually, right? Internally, it's not, because there is a variable that is changing type inside. And you will tell me, okay, if Julia was clever, we will stay in integer, okay? No, if Julia was smart, we will choose only float 64 as a variable type. But this is not true, because why we cannot rely only on float 64? Does anybody have an idea here? Because suppose you don't enter the loop function. N stays an integer in that case, okay? If you don't enter the loop, N will stay an integer. N becomes a float only if you enter the loop, okay? And this is the job of the parser of Julia, actually, when it compiles, to decide actually what is the best variable type you have to choose depending on your function. So normally, if you come from the compiled language word, actually, the easy way is to put it as float 64. So there is no choice, there is no thinking, no choice to do for the parser itself. In this case, you have a stable type for the function and the stable type for the variables also. Okay? So this is optimization. And optimization only on the variable type, because the parser here will have to think a lot. So you have this on a simple function here that increments r to r plus 1, okay? But in many complicated functions, actually, the parser have to do this work. And if you want to optimize your code, actually, you have to think of the type of your variables and also the type of your functions, okay? So if we had n as a return, so in the first example here, what we didn't put an n as a return. We did only r, okay? So if I put n as a return, my function will not be stable anymore, okay? So this is the tricky thing about having a dynamically typed language, but who's seeking for stability in behind the scenes. Is it clear for anyone? Sorry? Does it make a copy of n? Yes, it does make a copy of n. Yeah. I don't know. It's a good question. I didn't deepen the thinking to this. But this is a good example of what is actually typing for function and variables is. Yes, go ahead.
If the function always went to the loop, and it knew that it would always return a float, would the JIT make sure that it was a float every time?
Yes, 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 yes. But here you're like, let's how to say it in familiar words, you're tiring the parser and the JIT, okay? Because it have to think, so it's more a recursive word. And this is a simple function. If you have a recursive function, for example, it's like, it's a mess, it's awful, okay? Is it clear for everyone? Let's make sure this is very specific to this language, actually, because you don't have this. Python won't ask you for this. It will do the job. It will put as many types if it wants for the variable, and it will give you an answer anyway. Julia will think a little more to optimize, okay? So this has to be very clear for you. What are the types of the functions and what are the types of the variables, and how these variables will, the parser and the compiler will modify the variable type, actually, during the runtime of the function, okay? Yes, go ahead.
Can't we define n as a float in the argument of the function instead of convert into a float inside?
Repeat the question.
Can we define n as a float in the function arguments instead of convert n as a float inside?
That's a possibility.
It's better, I think, no?
Yeah, you can convert it inside the function, yes.
Okay.
And make sure that after, when you exit the function, it is correctly typed.
Yes.
But I mean, that's not done by the parser, it's done by you.
Yeah.
It's like defining the types of the variables correctly.
Okay.
Yes, go ahead.
Yeah, you said that we should treat it like a compiled language, like a statically typed, I guess.
Exactly.
Then why were we seeing this?
Just to explain you, for people who don't see it as a compiled language, because a lot of people, I did this mistake once, okay? Because I consider it as a Python way of coding. But
yeah, I mean, it's good to know what's happening. But
sorry?
it's good to know what would happen.
Yeah.
But this is not the recommended way to use it, as you said.
Yes, but it's a very good way for me to explain actually what is the static type of function and the static and what happens to the variables actually, independently one of the other.
Okay.
Okay.
Thanks.
Just to see actually when you exit a function, it doesn't mean that your functions is static for types. It doesn't mean that your variables are static for types. It's not the same thing because people associate type of function with stability of the type of variables, okay? This is not always the case in this kind of languages. Yes.
Maybe this defeats the point, the design decision of the language, but is there like a lint or a rule that you can turn on to give you a warning if you're not defining types in places?
No.
Okay.
Not to my knowledge, at least. Yeah. Okay.
If you define the type, it's static always.
Yes. Yes. Okay, so this is the conclusion of this part actually. Much faster for the parser to optimize the compiler time at the runtime. So change the type inside the function. So that's what the solution of your colleague said. So you do it yourself. You change it from int to float 64 to make sure it outputs the right variable. So, sorry? Not to my knowledge. Union for types works for 2 only, I think. I didn't see the case with three types, actually. In that case, if you go to the tree of the Julia variables, actually, it will go from bottom to up. You will go to any. So in that case, you don't know what type you have. But it always goes like that. So you go from the bottom to the tree to the up to the tree. So you always get you want to always to get far from abstract types. Okay. So on the variable trees that we saw before, you want to go stay at the lowest point of the tree. So Julia, the parser, we go from there to up. So it's kind of a decision tree for the parser, actually, for the variables. Okay. So we go to next part. So here, actually, we'll be switching to the CUDA part for the multiplication of matrices. So we have to change my runtime up, and we will get for GPU T4 up. Okay, so here we will bring the package manager in the notebook with CUDA.
Can we use GPU with Julia only for NVIDIA GPU?
CUDA is for NVIDIA GPUs only, anyway.
Oh, yeah, but my question was, can we add other packages to use Julia and GPU on AMD or Intel GPU?
I don't know if CUDA will work on AMDs, maybe colleagues. Nope.
No, but
so
can we use another thing than CUDA on Julia to work on AMD GPU, for example?
Yes.
Okay.
There is some library specific for AMDs. Yes, of course. Sorry? Metal is for Apple, actually. So Metal is for Apple. It runs with Metal. So, but it's not the CUDA. The most used one is CUDA. Let's be honest about that. You will find much more examples of usage of CUDA for parallel computing than AMDs or Metal. Okay, but we don't know what will be the future actually. So, okay, so here we insert the CUDA library. So what is the CUDA.gl? So remember here, I didn't put CUDA.gl. Okay, also it exists in Python. If you said just CUDA, expects CUDA.gl behind the scenes, okay? Because all these libraries actually has been recoded in Julia itself. So this is one of the most used one actually for parallel computing. It includes a lot of kernels and other second-hand libraries like the cuBLAS, cuRandom, cuFFT, cuSparse, and cuSolver. So these are native in the library itself. You don't have to call them by yourself. They're there. And for deep learning and AI, you have the CUDA-NN and the cuTensor actually that are implemented in CUDA.gl. So it's a very rich library, very well optimized. So now what we did, actually, we installed CUDA, but it doesn't mean that you have the library, that you have access to the GPU. You need that your runtime sees the GPU. So the first thing you have to do is to type device, okay? And here you have a Tesla T4 that is available for you. So you can do get some more other information about your device to make sure that it's available, actually. So this is one of the biggest issues you have sometimes in Linux environments, is the CUDA drivers, okay? Everybody here knows the NVIDIA SMI, okay, which is a nightmare because once it runs, you do something, it doesn't run again, and okay, so Julia actually have a native system to check this for you. And if I name this device, so this device, I can use it as an object itself, okay, with some methods. I call it the V, okay, and I can check the memory available. So this is why this is important, because you always need to know what is the available memory of your GPU actually before using it, okay? So the idea here is not to overload the GPU and to send data only on the available memory. Otherwise, you have to stream and to do some ranks to actually to handle the memory during the computing time, okay? And you can also know the maximum threads that you can send on the GPU. So this is information, the information is called attribute, and it will give you the number of threads that you can send in your GPU. So this is very important also when you generate your kernel, actually, the number of threads. Okay, so creating a variable on a GPU is very easy. You just put A equal cuArray. So we have the array function. We add just the cu extension before, and it's automatically created on the GPU. Okay. So I don't do this way. Okay. I always create my variables on the CPU. I handle the transfer to the GPU. I make the computing, and after I handle back to the GPU, to the CPU. Okay. Everybody has a way to work, because when you do this, actually, you never know where you created your variable. Yes, go ahead.
Do we have to put CU before everything native from Julia to?
It's a method, actually. So
okay.
It's in the documentation. You have to use that.
And
so normally there is a logic behind. So you take all the words that came from the Python libraries. You add CU before, and you can do. But it's not always the case. So.
But wouldn't it be better for the parsing to just put CU point? And
you can do that also.
Okay.
Okay. So just as we are running out of time, I will get into the matrix multiplication actually, but I will do it this way. So we will not create the matrices on the GPU directly. We will create them on the CPU, handle the transfer, because this is the job you will have to do actually when you're doing your program. You don't send data to the GPU directly. You have to create them on your CPU first, and after actually you send them to the GPU. So all this work of data transfer between the computing steps is done by you for the optimization purposes, actually. So here we define a dimensional matrix of n equal 10. So we create two matrices, A and B, on the CPU. So we use the random function to do this. Okay, so to answer once again your question, you have the cuRandom. So if I wanted to create this on the GPU directly without passing by the CPU, I use cuRandom on the GPU directly, and it works. Okay, it's faster, of course. Okay, but it's the same way to do it. So there is two ways to do it. So this is specific to the developers and how you want to make your code. So here we make a transfer of the variables to the GPU. Okay, So now all the variables are on the GPU. So we make the computing of the C matrix, which is the multiplication of A and B on the GPU itself. Okay. And after we did this, we transfer back the data from the CPU to the, from the GPU, sorry. So look, I did the mistake, from the GPU to the CPU again. And we display the results. So quite simple example, okay, on how just by well identifying your device, checking its memory, actually you can create easy matrices. So what you can do after this, actually you can modify n to 100, for example. Okay, and you can run it again. And you see it will not change a thing on the computing time because you're doing it at the GPU, on the GPU. Okay. That's easy as it is, actually, as you see it here. Okay. So I didn't give a CPU example because it's like Python is very, very basic, and you saw it last week, I guess, if I remember well. For the CPU, it was thoroughly flawlessly like Python. For the GPU, it's quite different. You have to use this specific CUDA library developed in Julia to do this, actually. And always be careful where you create your variable and what you're doing on it. So there is some, so the CUDA library gives you a method which is Q events that will allow you to monitor actually the computing only on the GPU. So it doesn't take into account the memory transfer, okay? If you want to do that, you have to use much more developed, complicated profilers to see all the transfer, because what you need to see is the computing time, but also the transfer time actually for it, okay? So the Q events method doesn't allow you to do that. Q events computes only the time, monitors only the time that you use on the GPU. Doesn't integrate the transfer of memory with it, okay? So you have to use the Julia profiler for that, and you can use also the add time and the B time that we used before actually to make the profiling, time profiling. I'm finished. Do you have any other question, Julia? So this is a rather quick introduction. Yes? It deals with, there is a specific library for that. Matrix sparse, I think it's called. Yeah, somebody told me about this a few days ago. So yes, so if you want to deal with this kind of problem, yes, it can handle it.
Some linear solvers?
Sorry?
Linear solvers?
There is linear solvers also integrated in the native library. It's really completely, all the libraries that you find in Python, you find them in Julia also. It's really, it's the only thing that is, so we didn't see the example here because we are in collapse. But for example, if you don't use any parallelization library in Python, like NumPy or whatever, you will be running on one processor, one thread, okay? Natively, Julia actually will use all the cores available, okay? So if you run it on your computer, you run Julia process or Julia code, you will see that it will use all the cores at the same time. If you do it with Python without any specific library, actually, you will be using one core only. This is the main difference, on the CPU at least, okay?
Okay, thanks.
So for Python, you have to use a multi-threaded library to get use of all the cores. In Julia, you don't have to do that. It uses all the cores natively.
Does it have something like matplotlib?
Matplotlib, alors, so this is the weakness of Julia. Plotting graphs, that's why I didn't do it. It's very, very slow. Let's be honest. That's why a lot of teachers don't use Julia, because if you take 2 or 3 minutes to make a plot, you lose all your students, okay? And I lived through this. That's why teaching with graphs and Julia, so something weird, if you wrap the plot library of Python, it's faster than Julia's. Okay. so Julia community has some work to do on the plots. I completely agree with that.
We can inside there just wrap it in Python and it's okay.
Yes, yes. A lot of people do this behind the scenes because the plot.gl is rather slow. And there is, if you go to the discourse link, there is like a debate like since 5 years on that. Why is it so slow? Why is it so slow? and it doesn't get faster. We don't know why. I think it's related to the runtime and the compile time, actually, for the plot library. And we think the slowness for the graphs are native to the language. So I don't think it want to go faster. So if you want fast graphs, wrap the plot library of Python and go with it. Don't use it with Julia. But this is an issue. I have one colleague that used to teach at Dauphine, and he abandoned Julia because of the problem of the graph of the plot function. So yeah, we have to be honest on this. This is not the best thing that Julia can do, making graphs.
Does it have HDF5?
Sorry?
H5? Does it has?
Yes.
Can we do some H5 writing?
Yes. Yes. It's native to the language also. Yeah. Like Python, actually.
Does it have, like, for example, multiplication between a regular and a sparse matrix? Or you don't know?
I don't know.
Okay.
Very specific use case. I don't know why people are speaking a lot of sparse matrices these days. People from the finite element community use this. We had these problems like for 20 years now. And it went under the carpet for like 5 or 10 years since the rise of AI. And now everybody is speaking back about sparse matrices. Why? I don't know. Is it a fashion or is it a hype? I don't know what is about sparse matrices. I think Vincent spoke about these sparse matrices. Sparse matrices, you find this problem actually in multiphysics finite element modeling because you have a lot of empty rows in your matrix. But now it arises another problem. Maybe Vincent will give some example.
Yes, so when I was asked in the winter, I was young and I wouldn't know. But now that I've taken some wisdom, we can use it for all kind of tessellation. When you have a space and you want to solve some equation,
yes,
you have to fill your space with simplexes. Okay. And then you will have the relation between each of the vertices of your meshing, and it will be represented by a sparse matrix.
Okay.
They are also used in sparsely connected neural networks.
So look, if IA is based on sparse matrices, it won't work, for sure. If what? If IA is being based on solving sparse matrices, it will be rather slow. But like in math, the sparse matrices problem is a problem we have like since 20 years right now. And every community has a way to solve it. There's no specific recipe to solve sparse matrices because it's really physics related. So I use it personally. I used to solve this through COMSOL multiphysics, which is COMSOL is a subsidiary of MATLAB actually. They separated like 20 years ago, 10 years ago. But it's yeah, sorry.
It's private.
Yeah, it's commercial use. Yeah, yeah. But it solves very well sparse matrices. I don't know how they do. They have, I think, patented solvers for this. So it's not open source. That's what I want to say.
No, it's a finite element commercial software.
Yes.
Yes. It uses some.
Yeah. Actually, finite elements comes to matrix solving problem actually, and matrix inversion. And there you have a lot of sparse matrices, especially if you don't work on one physics, you work on multiple physics. So if you combine fluid dynamics with induction, for example, or Maxwell equations, you have a lot of sparse matrices. And you need a solver that works well with these. And these are commercial ones, and they're not, they're really patented. There is patents about this, so you cannot use them actually. So you have to pay for these actually. Unless you take the standard ones, maybe the open source, but you have to wait a lot. So it takes time. Okay. So I hope this gave you a small insight of what you can do with Julia rather quickly. And if you want some more details, so I go back to my presentation very quickly. There is, in this link here, there is the presentation done by Philippe Gras 2 years ago when you have the implementation of Gray-Scott on Julia, on CPU and GPU. So it's all on this link. So you can have a very good example here of solving the Gray-Scott equation on the CPU and the GPU with all the memory transfer, the computing, and getting the data back, and generating the video, all the stuff. So if you want to see a good example, there is one already present, actually, and it's open, so it's open to everyone. Any other question? I didn't check this course. Oh. So do you see, I may maybe make a zoom. I have to take some time to read all this, sorry.
I think it's just the answer to Adrian's question.
Ah, okay. Okay, thank you, Adrien, for answering. So, bah, merci. Thank you.
Is this a presentation and call-up available somewhere?
I can share it, yes.
So we'll write you an email, or
Sorry?
we'll write you an email, or what? Where?
No, I will send it to the organizers.
Okay.
I will share. They will share it with everyone. So I will share the PDF and also the Jupyter notebook if you want. No problem.
Okay.